again. Okay, I need to update the shit. T1. Hello. 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 Okay. So we are live now, and it's Wednesday, December 10. 15 days for Christmas. 14 days for Christmas. And we are here solving some DP problems again. And today we will solve the fourth problem of the atcoder DP contest. Okay, so it is 41. Okay, so let's start with the knapsack problem. Let me get my the whiteboard ready. D knapsack 1. Okay. There are n items numbered 1 to n. Item I has weight W and value Vi. Taro is decided to choose some of the n items and carry them home in a knapsack. The capacity of the knapsack is W, which means that the sum of the weights of the item taken must be at most W. Maximum possible sum of values of item that Taro takes home. Okay. Also, it's a simple knapsack. Again, we'll do. I should make a template for this. I already have, but I don't want to use it. Instead, we'll make a DP template. I have the CP template with me, and it has a lot of boilerplate, so I don't want to upload that. I don't want to like use it here in the when I'm coding in stream. So we'll make one custom template. Okay, and then we'll make two vectors, and all of which size is n, and we'll take the input and wi vi. Okay, we have taken the input. So knapsack, for a knapsack, we have let's take this input as example. Why did it not copy paste? Okay, copy paste. So So we have the input, okay, and we see that we have the weights here and their values, right? 3, 4, 5, we have 30, we have 40, and we have 60, and the maximum weight limit of the bag is 8. Maximum weight limit is 8, so we can only take selected members in there. Okay, so how does knapsack work? So knapsack basically is choosing to put the item in the bag or not. So for every element, every item in the array, we have two options basically, whether we choose this or not, something like that. So for example, let me start from the last element. Okay, so we have this 3, 4, 5, right? Suppose I'm here right now and I choose to include it in the knapsack, or I choose to exclude it from the knapsack. So in case I include it in the knapsack, then the weight that I can carry the knapsack, it will be what? 8 minus 5, so basically 3. Okay, and the value that I have in the knapsack right now is 60. So again I'll be here, right here, then because I've already processed this, so I will move here. And if I did not take it, then I'll be here, and the value is 0 and the weight is still 8. Okay, so I have two options, right? And for processing 4, again I have two options. I take it or I don't take it. Okay, so in case I take it, right? In case I take it, then it will be what? But you see, I cannot take 4 since the weight is 3 remaining. So 4 cannot be taken, so I'll have to skip. Okay, so in that case I'll be here then with 3 and 60. Okay, so now I can see that 3 can be included in the knapsack, so I'll include it, and then the weight will be what? 0. Knapsack will be 0, and we have the maximum weight as 90. So 90 will be returned from here. Okay, 90 will be returned from here, and then it will return to here, and then it will return to here. So in the left side we have 90. Okay, in the right side, since the knapsack is still 8, right? So we can choose 4. So let's say we chose 4. We chose 4. Okay, so it will be 4, and we'll have the score as 50. Okay, this is 50. Okay, and we'll be here, or if we don't choose, then we'll have the weight as 8 only and score 0, and we'll be here. Okay, on 3, since 3 is less than 4, we'll choose to include it. Okay, and if you don't include it, then also there is case. In that case, we still have 3, and the answer is 60 only here. Okay, and the weight is still 3. So from every decision that I make, I want to maximize the value that I gain from it, right? So whatever decision you make at a node, we will choose the maximum out of it. Similarly, if I choose to include 3 here, then the weight will be 1 and will be at the beginning of the array, and the value we'll have is 80. Okay, if we don't include it, then the weight will be still, the weight still will be 4, we are at the beginning, and the value is 50 still. Okay, whatever maximum is from from the choices that we made, we will choose 80 to send back to the parent, and then it will then be returned to here. Okay, and here also for 8 also we have two options, include it or not. So 8 minus 3 is equal to 5, 0, 30, and here we don't include it, so it is still 8, 0, 0. Okay, so we'll go back, and 30 will be returned from here. We'll go back, so we have 50 and 30. Choosing maximum out of it, we'll return here what? We'll return here 50. Oh, sorry, we'll return here 80. We'll return maximum 80 here, since this is the maximum value. And out of 90 and 80, the maximum will be 90, so answer will be 90 only. So you can see how the DP will work out, the DP recursion will work out. So yeah, we'll make the DP state like this. Let's say we have DP I, N, and we have the what? We have the weight. Okay, so this is basically maximum value of knapsack till ith element where j is the knapsack weight. Okay, transitions will be this is the state. Okay, let's go for the base case. What will happen if we don't have any element and we have a knapsack? In that case the value will be 0. So whatever x that we have, it will be 0 for all x belonging to the for all x, let's say we're starting from 1, so for all x it's a 1w. Okay, similarly we have this case. What if we have elements but the knapsack weight is 0. In that case, the value that we can gain sorry, in that case the value will be 0 only, because we cannot put anything in the knapsack. Okay, similarly like this only. So this will go from 1 to n. Okay, so this is the base case, and we have the transitions. Okay, so whenever I'm at a dp and I'm choosing to process the ith element with a weight j, I have two options. Like this only. I'm going to consolidate base case with the general case. Okay. I or j. Let's not do it like this. I equal to 0 or j equal to 0. Okay. And it will be maximum of dp I minus 1 j. That means I have not included in the our knapsack, and dp I minus 1 j minus wi. It means that I have included it in the knapsack, and adding this with add this with our value that we have for that element. So this is the knapsack transition. Answer will be of course dpn, and j is the weight that we are given. Okay, I think it can be done in a linear dp as well. I mean yeah, a linear dp. I need to think of the transitions for this, and that can be done as well. Okay, for now we'll implement it. We have a dp dp size is n plus 1 vector and w plus 1, and all elements are initialized to 0, so we don't have to include that in the base case or in the loop. And I'll go from I is equal to 1 to n, and for j is equal to 1 to the knapsack weight. And I'll just do this. This thing, it also has conditions. So basically, if our j minus wi is greater than or equal to 0, that in that case only we can include it in the knapsack, otherwise no. So if j minus wi minus 1, okay, it's greater than or equal to 0, in that case only we'll do dpi j So the thing is that if we can include it in the knapsack, we also have the option of not including it, right? So yeah, that will give us more choices. So yeah, if this is the case, then we have two options: either include it, either not include it, or include it. Okay. And if it is less than 0, then we only have one choice of not including it. So yeah, it will be like this: maximum of dp I minus 1 j comma vi plus dp I minus 1 j minus wi, and else dpi j is dp I minus 1 j, and in the end we'll just print the output as nw. Okay, copy, paste, print 90. So yeah, it is working. Let's see this. Okay, so this is 5. Okay, let's see the DP table. 5 million. For this the answer should be 17. Okay, copy this, paste this, verify, submit. Wrong answer, runtime error, TLE. Oh fuck. Second knapsack, same. Okay, it's also the same, but this time we cannot take we cannot do n into w. Okay, this time we cannot do n into w, and the values are 10q, so there is that. So the maximum sum we can have is 10 to the power 5, so int. Okay, then for the weight part, knapsack with weight 10 to the power 9. Instead of storing it in the DP, can we do it in a map? Okay, let's try to do it like this. Okay, so we can try to use map. That is one thing I'm thinking of, but still we have to run the loop from 1 to n, 1 to w. So not sure about that. Other than that, can we? Okay. Save storage. To save the space, we, mm, I think there is a very standard way of doing this, but I'm forgetting it. I'm not sure. I do think there is a different way of doing this. Map sac when weight exceeds. Holy shit. If only I knew whatever this is, Russian. I think I should start learning from CPL algorithm. I've never tried learning from it, and it is a pretty good resource. Oh yeah, back to the topic. Yeah, I don't know how to optimize for it, but this looks good. We can do it here also. Okay, decreasing order so that fj minus wi implicitly corresponds to fi minus 1 j minus wi. What does this mean? Okay, this means that if that element is not updated, it will be the last row's answer, not the current rows. Okay, so we are starting from the last one so that we are not updating w minus ji first. If we update that, then it will be I j minus 1. Okay, so we can get rid of this dimension then. Okay, we got rid of that dimension, and again and if we start from wt, so in that case we don't have to check the conditions as well. That's kind of smart, and yeah, we can just remove this and also remove this. Thus we have the segmentation fault because we cannot store this many number. Instead of this, to map. The answer is 10. What about this? The answer is 17. I'm sure we are going to get TLE or MLE in some cases, but yeah, let's just try to submit it. TLE, MLE, TLE, MLE, TLE, MLE, TLE, MLE. Okay, TLE. TLE. Second test case TLE. Okay. Okay. Least weight you need to carry to get a value of this. Okay. So instead of going from we are done with this question. So we are here. So here the question is the what maximum value of knapsack maximum value of knapsack within total weight less than equal to W, something like this, right? So we are going to convert this into least weight carried in knapsack given total value least least weight carried in knapsack given total value. Okay, so yeah, this is our new dp state. So our dp will be now dp I j, so it will be what minimum weight carried till ith element given total value is j, and similar to the transition will be like that only. If you can copy this, or no, okay, let me do it. Or we have dpi, which is basically minimum weight carried given total weight is I. Okay, and the transition, the first base case dpi will be maximum, so int max for all I, what 1 to total value. Okay, and the transition will be that dp of I is minimum of dp of I comma dp of I plus minus vi vj plus we have the weight. Okay, so this is the transition, and answer will get for answer is basically I such that dpi is less than or equal to the weight constraint, and yeah, this is the maximum that we can get. Okay, yeah, and I will go from how do I iterate? I is equal to 1 to total value. Man, I need to learn discrete mathematics again. So this is how we'll do it. Okay, so we do it like this. Okay, again I learned something new and pretty good. N plus 1, no n plus 1. We have int total val is equal to 0, and we have this total val plus equal to pi, and this is simply total val plus 1 comma 0, not 0, we'll do it max, and we'll just run a loop. Int I is equal to 1 to n, and int I is equal to 1 to total value I plus plus. We want to run it in the opposite direction because we don't want the ij minus value to be considered in the next state, in the current state only. So yeah, like in the previous example that I explained, similar to that. So, and here, okay, so we'll go from j to vi and j minus minus, and here we'll just do dp j is minimum of dp j and dp j minus vi and plus wj. Okay, and answer will be answer is 0 for int I is equal to 1, I less than equal to total val I plus plus, I plus plus, and if the dp is less than equal to the weight, in that case the answer will simply be I. And we'll just print the answer. Okay boy, 1e9. Okay. So why 0? Okay, it is I. Okay. What is the appropriate base case? Total value is 0, then it is 0. Okay boy. Go. Wait a second. Please run. TLE, MLE, TLE, MLE, wrong answer. TLE, MLE, wrong answer. Damn, workflow. Yes. So if we want to make a 2D DP into 1D DP, and if you see that the DP state is only say DP state is only dependent on I minus 1th state. So you can try to convert it into a single state by just reversing your inner loop, and then yeah, it will work. LCS. Okay, so it's LCS only, right? Can we do LCS in 1DDP? I don't think it is possible. So we are here. We have two strings. String what? S and T will take input. Okay, take another input. Okay, we'll define the dp and we need to return the string, right? Okay, we need to return the string, so we need to create string at the end. For that, yeah, we can do that later, but first we need to calculate the longest common subsequence. Okay, so what should be the base case? So I think it is 0 only. If any one of the string's length is 0, then that is 0, and if both are 0, then also it is 0. Okay, run the loop. LCS I don't need to explain because we already have solved problems in LCS. That is why I'm not going to my whiteboard. Yeah. And should we do this? Again, if we see that Si minus 1 is double equal to Ti minus 1, Tj minus 1. In that case, we have two choice for Ig. It is I going to, oh no, we have only one choice, and that is 1 plus dp I minus 1 j minus 1. Else we have two choice. dpij is maximum of dp I minus 1 j or dpi j minus 1. Okay, so for the final string we can do okay, when I is equal to n, j is equal to m, and while I greater than 0 or j greater than 0, or rather while dp I j is greater than 0. So if we have s I double equal to tj minus 1, then we'll just do answer plus equal to answer plus equal to si minus 1. Else, okay, we need to do this also, I minus minus j minus minus. Else we have two options. Okay, we have two options. If I is equal to I minus 1, if I is equal to, we need to check. Okay, no. If I dp I minus 1 is j is greater than dp I minus I j minus 1, then in that case we'll go to the this else I'll go to this. Okay, I hope it works. Let's see how to answer. BXC. Okay, we need to reverse it. Reverse answer dot begin end. AXP. Okay. This Ardara. Copy, paste, verify, submit. Wrong answer, time limit exceeded, memory limit exceeded, something please. Wrong answer, longest path. Okay, I think we are done here today. The next is a graph TP, so we'll do it tomorrow. And yeah, we learned something today, and for like more advanced stuff, I'm thinking of going to that CP algorithm website. And yeah, that was it for today, and we'll meet tomorrow with the graph problem, and we'll try to solve again 2 to 3 problems. Yeah, that was it from my side, and I hope you have a very good night today, and peace.